In this video, we're going to begin to discuss what I call Intro to 2D or Intro to Two Dimensions. What is meant by that is we've worked with a lot of equations that have a single variable, and so that would be a one-dimensional equation. Now we're going to be working with equations that have two variables. And so that moves us to two dimensions, and when we move to two dimensions, we start doing a lot of graphing on what's called a coordinate plane. I have one on the screen here. I'm going to go through and kind of talk about just the different parts of the coordinate plane so that you understand the vocabulary I'm using as I talk through graphing and working with two-dimensional equations and whatnot. So you might recall that we did some graphing earlier where we, when we solved linear inequalities, we graphed things on a number line, and so that would have been a one-dimensional graphing where it was just a number line, and on one side were the positive numbers, one side were the negative numbers, and then in the middle was zero. Always had you label zero in the middle, and we would just shade it left or right. Now what we're doing when we go to two-dimensional graphing is we've taken another number line and intersected it. So we have a number line for each of the variables. The way I have this set up here, the x is the number line for the x variable will be the horizontal axis. The number line for the y variable will be the vertical axis. And with the vertical axis, the positive numbers are up and the negative numbers are down from the point where it intersects with the x number line or the x-axis. Okay, so that point at which the two number lines intersect, that's going to be the 0 for both of the number lines. So that's where you would start counting for the x number line. You would count 1, 2, 3, 4, like that, or -1, -2, -3, -4. Now you wouldn't actually put the points. I'm putting those so you can see what I'm doing when I'm counting. And so if you're counting off values for the y variable, you would go up 1, 2, 3, 4, and so on, or down -1, -2, -3, -4. And again, you wouldn't actually put those points. I'm just showing that so you can see where I'm actually counting, so that you can't see me pointing. So I'm going to clear all this out, and we're going to talk about some other specific parts of the grid. Alright, so what I've been calling the x-axis, and I think it slipped out at least, this x number line is called the x-axis. And similarly, this one's called the y-axis. We won't always have x and y variables, so sometimes I'll refer to it as the horizontal axis and the vertical axis, or if the variables change, it may be like the t-axis and the p-axis or whatever. But it's always the axes is what we don't call them number lines, we call them axes. One important thing to note as we change the variables and whatnot is that the independent variable is always graphed on the horizontal axis, and the dependent variable is always graphed on the vertical axis. And I'll talk more about what's meant by the independent and the dependent variable here in a second. But just for now, just note that the independent and the independent is on the horizontal axis, the dependent is on the vertical axis. Then as far as the points that we put on the graph, so like let's say I'm going to count off 3 for my independent and 2 for my dependent. In this case, 3 for my x and 2 for my y. That creates a point, but the way we show that numerically is something called an ordered pair. And it's called an ordered pair because the x variable will always come first and the y variable will always come second. So it's ordered in that way. If we weren't using x and y's, the independent variable always comes first and the dependent variable always comes second. So then that point I plotted, I could represent in order pair notation as 3, 2. You have to have the comma and you have to have the parentheses. They're all a part of the notation. So then with this point in the middle that I told you about, I said that was going to be where both variables are 0. We would represent that with the order pair 0, 0. And this is called the origin. And I'll refer to it as that frequently. So I just want to make sure you know the words that'll be coming out of my mouth. So that's the origin, because that's where we originate our counting. Now let's say we have a graph on our grid. So I'll just sketch one in here real quick. I'm going to sketch it in green so it looks different than all the other stuff that I've written on here. I want to emphasize that there's the grid that we're counting things off on, but we put graphs on a grid. So the green part would be the graph. The grid is not the graph. The graph is the stuff we put on the grid. So there's two special points with most graphs. We'll have these. It's not always necessary, but there's the point that it crosses the y-axis, and there's the point at which it crosses the x-axis. And these are emphasized for various reasons, as you'll see as we begin covering this material. And because they get emphasized a lot, they have special names. Where it crosses the x-axis is called the x-intercept. And where it crosses the y-axis is called the y-intercept. We're going to talk about those a lot and learn how to find them. Just really get familiar with these ideas of the x-intercept and the y-intercept. So those are kind of the basic things I want you, the basic language of this grid that I want you to know. There are other things that I'm not too concerned about, so this is the language that I will be using frequently. I do want to caution you and encourage you about listening, about how you listen to the words as we move forward, because once we start graphing, everything will be an x something or a y something. So for example, here we have an x-axis and we also have an x-intercept. And what I've noticed is that sometimes people will just listen to the x part, or we'll have a y-axis and a y-intercept and people just listen to the y part. But the y part is just telling you whether it's related to the independent or the dependent variable. It's the second word that actually tells us what we're talking about. And so just because it starts with an x doesn't mean it's the same as everything else that starts with an x. So make sure you're learning that second word, like axis and intercept in this case, and there'll be a lot more. And also make sure that you're listening for that and using that when you talk about it. Okay, so what I want to do now is talk about this idea of independent and dependent variables. All right, like I said, the x, when we use x and y notation, the x is going to correspond with the independent variable, and the y will correspond with the dependent variable. Now the letters may change, but whenever we use x and y, we tend to use those for our generic ones. The x will always go with the independent and the y will always go with the dependent. Now the reason that this makes that order matters is because the independent variable will cause the dependent variable. So there's going to be this cause and effect relationship between the x and y. It's not just that the x is first, it's that the x causes the y. And sometimes we'll say input, output. You put in an x, you get out a y. Now, so far it's all been very generic, but you know, when we're doing this math, we're really doing it, or its intention is to wrap it in a real world context. So in a real world context, it might be something like the hours you work causes the pay you receive. So it's it's necessary that the hours you work would be the independent variable. It would not make sense to make pay received the independent variable, because the pay you receive does not determine the hours you work. That'd be a very bad way to run a business. Similarly, like, you could talk about the age of a child and their height. How tall you are does not determine your age, but usually as you age, you get taller as a child, and then you stop eventually, of course, and then you start shrinking eventually. Yep, that's what happens. So anyways, when we're talking about independent and dependent variable, this is why it matters, because when it's wrapped in a real world context, the independent variable will cause the dependent variable. Sometimes the language of independent and dependent is confusing for people. In particular, independent. And so I like to say it's not so much that the independent variable is completely and totally independent, because everything has connections in life, right? It's more that the dependent variable is dependent on the independent variable. So for example, the pay you receive is dependent on how much you work. Now, how much you work isn't just completely independent. Your boss probably determines that. So that's where, like, when people start thinking about it in context, they're like, well, it's dependent too. But it's, of the two things we're looking at, one causes the other. There's every once in a while a situation where it could go either way. It's truly like a back and forth sort of thing, in which case you could choose which one you want to be your independent variable. But in most scenarios, there's clearly a cause and effect relationship, and the independent variable should be chosen as the thing that causes the dependent variable. Alright, now I'd like to clear this out. I just noticed that there's no put here. Output. There we go. It's all better now. I'm going to clear this out, and we're going to talk about different ways of organizing information. Alright, so a lot of people refer to everything we're doing as graphing, but graphing is just one way of organizing the information. These units that we're going to be covering from here forward are not just about graphing. They're about two-dimensional relationships, and one way to represent that information is through the grid that we saw above. But there are other ways as well. So ordered pairs are a way to represent the information. So let's go back to the hours worked and pay received example. Let's say I get paid $10 an hour. So if I work 1 hour, I get $10. So that is a way to represent information. As long as I know what context it's in, I don't have to label that or anything. I just automatically know what those numbers mean based on the context I've been given. And then, if I work 2 hours, I get $20, and so on. So ordered pairs is one way to present information. Another one is tables. Now, there are lots of different ways to build tables, but the ones that we will be looking at a lot are these things called XY charts or T-tables. And so just to do the same thing as ordered pairs, it's just in table form. You can do a graph. Now, we've seen and worked with the one-dimensional graphs when we did inequalities, right? But you can also have these two-dimensional graphs, like the quick sketch I made above, something like that. Just thinking in terms of pay received. If I work 0 hours, I get $0, and it goes up from there. Now, another way to represent that is really useful is an equation. So, I forgot to write the word graphs. So, like, if I wanted to do my $10 an hour as an equation, I would do y equals 10x. So if I work 10 hours, if I work 1 hour, I get $10, and so on. Some people are sometimes bothered by the order I put this in, so we can talk a little bit about that. Because according to the story, it's like, the story wouldn't even work that way. If I put the x first times 10. So if I work 1 hour, I'm going to multiply that by 10 and then I get 10 bucks. If I work 2 hours, I'm going to multiply that by 10 and I get 20 bucks. And so if you do it in order of the story, you get this x times 10 equals y. But that's not what we're doing. When we write an equation, what we're doing is we're defining what y is. So when you define something, you always put it on the left. So we're saying y is 10 times my input. So the money I get out is going to be 10 times the hours I put in. And so it's always set up with the dependent variable hanging out on the left there, because we're defining the dependent variable based on the input or the independent variable. So another way that we've worked with with equations is using function notation. And so that's another way we'll see the equation work. And we've worked with the mechanics of using function notation to put values in and get values out, but now we're actually going to talk about it a lot more as far as how it works and what it means, and all of those details that I've kind of been glossing over up until this point. Okay, so that's what we're going to turn to now. Is I want to just review function notation and kind of add some sophistication to it. So let me clear this out. Alright, so function notation is something we've worked with, but I haven't really unpacked a lot of its nuances. So I want to start doing that. So let's say we have an equation with two variables, something like y equals 2x plus 3. Okay, so you can have it in two variables like that, where x is our independent variable or our input variable, and y is our dependent variable or our output variable. So this is saying our dependent variable is twice our input plus 3. Now we can use notation, function notation, to express that exact same thing. So when we do that, we get f of x equals 2x plus 3. So in terms of the x and y culture, the f of x symbol is equal to y. So, and that's a substitute that you can take to the bank. F of x, or the dependent variable, is equal to, f of x equals the dependent variable function part. Now, I want to break this symbol apart a little bit here. So we say f of x, or a function of x, but the x here is our input, like we saw when I unpacked all of that. And then the entire symbol here, the f of x, is the output, because again it corresponds to the y like we saw up here. The f part is the name. Sometimes people treat f of x like it's the name, but the f is the name. So the name of the function is f. It's a function of x because that's what we put into it to make the machine work, and the output we get is f of x. So the output is always base defined on the input, because that's how it works when you're dealing with two-dimensional systems. So we've done the math on this, but with this function I showed you there, if I wanted to do f of 5, then that's going to equal 2 times 5 plus 3, so f of 5 equals 13, right? And so that's how we, oh, I changed that to an x, like I'm always picking on you guys for doing. So f of 5 equals 3, and this corresponds to the order pair 5, 13, where the input's the first thing and the output's the second thing. So you can do it with function notation, or you can do it with an order pair. And I'm not telling you that when I ask you to find f of 5 that I want you to write the final result as an order pair. You would just write it as f of 5 equals 13. I'm just showing you that it corresponds to an order pair so you can make that connection there. So we've done a lot of work for function notation, so I'm not going to do a lot of examples. I just really, what I feel is new here that I want to emphasize for you guys is that your dependent variable, in this case y, is going to equal your f of x, and then all of this relationship here, where now we're thinking about the stuff in the parentheses as our input, the entire the output is the f of x and the function name is f. So if I had g of x, g is the name of the function, g of x is the output of the function. Okay, so now that we've gone through all that lingo and everything, what I want to do is change gears, and I want to show you some basic graphs that you just need to be able to recognize. So this is going to be kind of a memorization activity. There are certain graphs that are kind of standard in math, and you're just going to have to learn all these standard graphs and their names. So let me pull that up. Alright, so here are the graphs, and there are several of them. I only have 3 on the screen right now, but there's going to be more. Let me just scroll down so you can see. There's several of them down here. We're going to talk about each one of these in turn. And basically, each one of these graphs represent kind of a basic graph in math, and what I'm wanting you to do is to be able to recognize the function equation and relate that to the shape of the graph. Okay? This part here where it says d equals and r equals, we're going to talk about that later. So I'm just going to jump over that and leave it blank and kind of write in some of my explanations over here. So this first one, each one of these has a name, and you need to know the name of the graph classification. So these are like classification names. So this graph in particular isn't called this, but the classification of graphs are called constant functions. So constant functions, they graph out as this horizontal line. Now this one is f of x equals 3, but a constant function is any function that's just equal to where the output's just a number. So another thing I'll do is give different examples of these functions. The one here is f of x equals 3. You could have something like g of x equal to a -7. So that would be a constant function going through the output value of -7. So a horizontal line going through -7 on the vertical axis. Okay, so that's the constant function. We'll look at the next one here. These here, so again, this is just an example of these types of functions, but the classification is linear functions. Now with linear functions, their graphs are called lines, specifically. And so a linear function is any function where the x, the variable, the input variable, is to the first power. Okay, wherever it lands in the equation or the function, it's to the first power. And if that's the case, it's going to graph out as a line. We could also say with that is it's any degree 1 polynomial function. So an example of that would be something like k of x equal to 2x plus 5. So it could have other numbers and whatnot in there, but the variable in it is always going to be to the first power. Alright, so the next one we have down here has x squared, and we've talked about x squared, and so this is going to use the same naming. These are called quadratic functions. And with the graph of quadratic functions, we call these parabolas. It's spelled like parabola, but we say it parabola. And so quadratic functions, the graphs are always going to be called parabolas. And what that means, the shape is this U-shaped, this soft U. Now it could be opening down, and it can move to other places on the graph. But if it's a quadratic function, it's going to have that U shape. The way you identify a quadratic function is it's going to be a degree 2 function, or any function where the highest power on the input variable is a 2. An example of that would be something like r of x, just like to use a little bit of variety here, equals like 2, well 2 we've already used as a coefficient, that's boring, -3 x squared plus 5x minus 2. So it can have an x to the first power, but it's going to have an x squared and nothing higher. And so when we graph this guy out here, it will shift around on the graph. It won't be in the same place as this standard parabola, but it'll still be a parabola, and we know that. And so that's what I'm wanting you guys to be able to do, is to look at a jumbled equation like this and know, hey, that's going to be a parabola. Alright, next down the line, if you're noticing the pattern here, we have x to the third, and so these are called cubic equations. Or I'm calling, these are all functions, so cubic function. Okay, and when we graph those out, it's gonna snake. I call these don't have special names like parabola and lines. The rest of them don't have special names for the graph, but I call these the snaky graphs. Now, the snake may go in the other direction, so it could snake up to the left and down to the right, but if it's a cubic function, it's going to snake like that. So the way you identify a cubic function by looking at its equation is it's going to be a degree 3 polynomial function. And an example of that that's different than just the standard one here on the left I need to think of a letter here. It's the most important part. Let's go with w of x equal to like a negative 5 x to the third plus 2. So it's going to be shifted around and stuff, but that will graph out as something that snakes, like our example here. Alright, so moving on, the next one here, these little things here, these little straight up and down bars, those are absolute value bars. We haven't looked at them much in this course, but just to remind you what those are absolute value bars, and they take any value that's inside of it and give back its absolute value, which is its positive value. It's not concerned about whether it's positive or negative, just the strength of the number, so to speak. So this function is called the absolute value function. And I should clarify, it's the function classification. They're absolute value functions. This is just the standard example of that. And the graph here is going to be a hard V. Now, like I said with the other ones, it could be flipped over and it could start somewhere else or whatever, but it's going to be a hard V. And I want to contrast that with the parabola. The parabola is a soft U. If you drop a marble in it, it will go back and forth. The absolute value function is a hard V. So if you drop a marble in it, it'll bottom out and stay put. And so when you're graphing these, you will be assessed on whether or not you get those shapes distinctly different. So if you graph a parabola as a hard V, it will be incorrect. And then the way you identify an absolute value function is it's going to be a function where there's an x inside of the absolute value function. Okay, so with the x inside of the absolute value, what we're going to be looking at is linear expressions of x. So an example of that might be something like m of x equals -2 absolute value of x plus 3. So you can have stuff outside the absolute value, but inside the absolute value is going to be an expression that contains an x, and it's going to be linear for the ones that we look at in this class. So that's how you can identify the that a function's an absolute value function, and that it'll graph out as a hard V such as this. Now I want to talk about the shapes here a little bit to kind of give you a sense of why the shapes are what the shapes are. So jumping back up here to the quadratic functions, you know, if I take this is going to square all of my inputs. So if I have like a 1 squared, then that equals 1. If I have a -1 squared, then that equals 1. So when I square opposites with a quadratic function, I'm going to get the same output. Okay, and if you think of when you're reading a graph, think of going left and right as your positive, negative directions on your input. So if I put in a positive number, I'm looking in this direction. If I put in a negative number, I'm looking in the left direction. And then as far as output, if my output's positive, I'm going to be up, and if my output's negative, I'm going to be down. So it'll be good for you if you can start processing graphs in kind of that more big picture sense instead of just the details of plotting points. So what we see over here is that when I put in a positive, I get out a positive. But also when I put in a negative, I get out a positive. And so that's why we get the symmetry on the graph of, regardless of if we're putting in a positive or negative, our output's going to be positive. And so we get this positive symmetry of the graph opening, both opening in the same direction. Whereas down here on the cubic function, if I have a 1 and I cube it, I get out a positive 1. But if I have a negative 1 and I cube it, I get out a negative 1. And so if my input is positive, my output is positive. If my input is negative, my output is negative. And so that kind of, you can see the motivation on the shape of that. The shapes aren't surprising. They're a result of math, which happens to be logical most of the time. No, I'm joking. It's logical all the time. Okay, now with the absolute value function, again, the absolute value function it's going to take any negative number and just consider it as its power. So it's going to take the sign away. So if I take the absolute value of 1, well, that's going to be a 1. But if I take the absolute value of a negative 1, that's also going to be a 1. So you get the same behavior that you would get with a parabola, except it's going to be this hard V behavior. And if you look at it, this is like what we had up there for our example of a line, except that piece that's going down negative is forced up to the positive with the absolute value graph. And so that's why you end up with that V, is because it's going to take all that negative output and force it up to be positive, and so you get that V shape. So I just wanted to go through that a little bit so you kind of have something to argue with yourself about on why these are shaped the way they are, and you're not just memorizing blindly. Okay, we'll move on now. So the next one's a square root function. And that's going to be any function where you have x inside of a square root. And I call these rocket launch functions because I think it just looks like a rocket's shooting off. And it may be flipped. It could shoot in the other direction. It could shoot down. But if you have x inside of square root, it's going to shoot off in one direction or another. I didn't give you another example of an absolute value function here. Absolute 2x plus 5. So basically a linear equation inside of an absolute value. Square root functions has x's inside of square root. When I say x, you can think just input variable. The input variable may change, but it means the input variable. So k of x equal to, you could have stuff outside the square root, but inside the square root you're going to have a linear expression, and that makes it a square root function. Alright, the last one's kind of crazy. Let me scroll down here. It's kind of going all over the place. These are called rational functions. And with them, the graph splits. This is the standard rational function. It's called the reciprocal function. You don't need to know that. You just need to know the classification, which is rational functions. And that's going to be any function where x is in the denominator. And if you think about this, we talked about our restricted values or our excluded values. Here, x cannot equal 0, right? And that's what's, x would equal 0 here would be right on the y-axis is when x equals 0. So the graph splitting like that is the graph avoiding division by 0 is one way you can think about it. And so with rational functions, you're going to have these splits in the graph where it's kind of excluding those values of x that would cause division by 0. And these can get really fancy. So another example of this could be, you know, the numerator doesn't matter, so we'll do a boring numerator. So if you have, let me make that a minus, something like that, that's going to be a rational function as well, because we have x's in the denominator. And these, I'm not graphing the ones I actually have here, but you may have seen these. These are oftentimes thrown on posters when they're trying to make fancy looking math posters. They'll throw these graphs on there because they get kind of fancy looking, but you have these dotted lines, and you'll dotted lines this way, and it'll swoop this way. Over here it'll swoop this way. Then you'll have something that snakes kind of like that. It's just going all over the place. The good news is we're not graphing these in this class. I want you to be able to recognize them. So if I give you a rational function, you can say, hey, that's a rational function. Or if you see a graph of a rational function, you can say, hey, that's the graph of a rational function. But coming up with the graphs ourselves is beyond the scope of this course. But they're cool. So as far as what I'm wanting you to know at this point is I want you to know that if I give you a function rule that looks like this, you can say that's a constant function and it goes to the graph of a horizontal line. Any constant function. So, you know, if I give you this function rule, you would know, hey, that x is to the first power, so that's going to go to the graph of a line, and we call that a linear function. So I want you to know the name of the function classification, and if I give you any of the variations, you'll know that it goes in that classification. Not even necessarily this, but if I give you any function that has an absolute value of x, you're going to know, hey, that's an absolute value function, and its graph is going to look like a v. So I want you to be able to correspond those three different types of things. The basic motivation there is once we start graphing these, and we will graph all of them except for that last one. Once we start graphing them, if you don't know what shape you're aiming for, you're not going to be able to get it graphed. So if I give you this function rule and you think you're making a rocket launch graph, then you will make a rocket launch graph, because you will hit what you're aiming for whether or not it's the right thing to be aiming for. So I want you to know the correct shapes that go with the correct function rules and then these classification names. Alright, so go ahead and work on that. This is one of the few times in math where I tell you, you just need to flat out memorize this stuff. So work on memorizing all of these different basic graphs, what they look like, what their names are, and how it is you can recognize them just given the equation, or what I've been calling the function rule.